Good afternoon to everyone, and a warm welcome to all of you. Thank you for joining us in this year's International Open Access Week lecture, being organized jointly by the DST Center for Policy, Policy Research, Center for Society and Policy, and the J.R.D. Tata Memorial Library. A special welcome to Professor Govindasamy Bala, whose lecture we are here for. International Open Access Week is a global event now entering its 15th year. It is an opportunity for all open access and open science advocates to engage in discussion and also inspire wider participation in making open access and open science the new norm in scholarship and research. I have the pleasant duty of presenting a short summary of our own involvement in this International Open Access Week program. It's an international program. There are such events that are being held all over the place, especially in academic institutions. So at our center, we have benefited enormously from Professor Subbaya Arunachalam, who joined us as a visiting professor in 2015. And he, along with another colleague, Mr. Madan Muthu, played a key role in catalyzing our interest in open access and also nudging us into participating in this International Open Access Week by organizing a set of events since 2017. And we have been doing it every year since then. And this is the 6th such edition. And so among the many events that we have organized so far, the event that we hosted in 2019 was a major landmark. It was a keynote lecture by Professor Vijay Raghavan, the then Principal Scientific Advisor to the Government of India. In his lecture, he emphasized the importance of open access for everyone, especially for countries like India. He also reiterated in his lecture India's strong commitment to open access. The discussions that he initiated in that event find an echo to this day in the ongoing efforts by the Indian government to formalize a coherent strategy for promoting open access for the country and for the country's researchers. Due to the pandemic, our open access related events went online for 2 years, but we are glad to be back with an in-person event this year with this lecture by Professor Govindasamy Bala, who is currently a professor at the Center for Atmospheric and Oceanic Sciences at the Indian Institute of Science. He received his PhD in Atmospheric and Oceanic Sciences in 1994 from McGill University, Canada. After 2 years of postdoc at Princeton University, he served as a climate scientist at the Lawrence Livermore National Laboratory in the US between 1996 and 2008. Professor Bala's main research interests are in modeling global climate change, carbon and water cycles, climatic effects of land cover and land use change, solar geoengineering, and global and regional monsoon systems. He has published over 110 journal articles in these areas. He is the recipient of the 2008 Scopus Young Scientist Award for Earth Sciences. He and his collaborators from China and USA won the prestigious, I have to get the name right, Norbert Gerbierbaum International Award from the World Meteorological Organization in 2014 for their research paper on fast climate system adjustments. Professor Bala has served as a lead author in the 5th and 6th scientific assessment of climate change by the IPCC. He was a member of the scientific steering committee of the AIMS Global Research Project. AIMS stands for Analysis, Integration and Modeling of the Earth System of a Future Earth, the organization, during 2016 to 2021. He is currently a member of the Earth Commission constituted by Future Earth to identify the safe and just corridor for a resilient planet. Professor Bala has also served as an editor of the journal Earth System Dynamics during 2010 to 2022 and is currently a member of the editorial board of the Institute of Physics journal called Environmental Research Letters. One of the reasons why we approached Professor Bala for this lecture is because of this year's theme for the International Open Access Week. The theme is Open for Climate Justice. And we could not have asked for a better person than Professor Bala to give this lecture, especially since climate science is one discipline where openness, when it comes to data sharing, is a norm rather than the exception. That is not the case in many other fields. Many of you must be representing different fields of science and technology in the institute. That is definitely not the norm, but this is the norm. And we were very interested in figuring out, in learning more about how this culture even got its start in this field. And he says this is the culture that has been prevalent for more than a century or so. So we are very keen to listen to Professor Bala about both climate science and the culture of openness in data sharing in that field. So with those few words of welcome, I now request Professor Bala to give this lecture. Thank you so much.
Yeah, thank you, Professor Abhinandanan, for a generous introduction. So in fact, I am actually a little worried that I may disappoint the high expectation that he has set. The reason is when he contacted me last week, I was trying to push it back. I didn't really want to give this presentation because I am not an administrator. So I have not really, I know open access, but it's just mostly reading in the science magazines, articles, and things like that. So, and also, 1 week is too short a time to do a exhaustive research on open access in the climate science area. And I know when we talk about open access, many of us think about journal access to the, the newspaper, the journal articles and etc. So I actually was thinking, I've been actually associated with climate change research, and I do modeling. And in fact, I've been using a model that is not developed by us, a model that is developed in the US, National Center for Atmospheric Research, by NSF mandate. NSF is National Science Foundation in the US, which funds, analogous to the DST here. They actually, by mandate, they have to actually throw that model open access. So anybody in the world can actually download this very comprehensive climate model and actually run. So I've been doing it. And at the same time, there is this, some of you may have heard about this term that is model intercomparison project. So this has been going on for almost now about 15 years, actually 3 decades. I'll come to that. So I realized, I thought, okay, maybe I can give a talk about this model intercomparison exercise. In fact, one of the main reason for this successful assessments from the Intergovernmental Panel on Climate Change, that is this IPCC, is because of this CMIP. That's what I believe. So let's actually go to the outline. So what I'm going to do is, in fact, I really didn't want to talk about actually in the beginning open access. I really wanted to talk about climate science as assessed by the latest IPCC report. So anyway, so I kind of mixed things, the science, model, data, and finally the open access in the form of MIP. So so what I did was, I'm going to give first a brief introduction to, to this field, very, very brief introduction. Basically explaining the key terms. And then, few slides on the simple key messages from the latest IPCC scientific assessment. And then there are 3 pillars for this assessment. One is the observational data. Second is this model. And third is this model intercomparison project. We call this as MIPS or MIP, okay? And then lately, there is an expansion of this MIP to, many, in fact, impact assessment. And I think that it has become too hard to track these MIPS. There are so many MIPS now. So I'll just come to that. So I think I just before, because this is climate science, I want you to be aware of two things here. One is what we do, the assessment of the science of climate change. And I think you got to be careful. In science, objectivity is very important. There is, whatever results, it should be reproducible and it should be independent of, who is doing it. And whatever claims you make or results, it has to be independent of the observer. But interestingly, what comes out of the climate change assessments, they have huge implications for the society and policy, how we actually make policy today. I mean, that's why all over the world you hear, how whatever policy the government is setting, how that's going to be in line with future climate change, right? So, but here there are problems. The objectivity is lost, right? For example, in social sciences and policy, right or wrong, it really depends on whom you talk to, or benefits or risk. In fact, I can tell you in the scientific assessment report, we don't even use the term risk, or this is the scientific assessment I'm talking about. Risk or benefit, we don't even talk about, because even that depends on who is actually going to benefit from climate change or who is actually going to face risk from climate change, right? So because of this dilemma, I think even 30 years back, the first IPCC assessment report came out in 1990. Even at that time, they were mandated to be only policy relevant, and they were not asked to be policy prescriptive. They're not supposed to tell the governments what the government should do. Instead, we just make the assessment. It's for the governments to make the policy, or a community of the countries to make the policy. Okay, I think this is important. That is why there is so much news. You see, is this really true? When you read in the newspapers, there are a lot of unproven things that comes out, right? So I want you to be very aware of this problem in climate change discussions. Okay, now I think it is actually good to put the take-home messages before what I am going to say, because you will at least know what I am going to say, right? So first thing is, I underline this term here, global, because this talk is of course going to be about global climate change problem. Okay, so global observations and models play a key role in our assessment of climate change. Okay, so if you take the IPCC report, it's mostly about global climate change. Okay, although there is also discussion on a little bit about the regional climate change, but these reports are all about global. So they really need global observation. If you are going to talk about global problem, you need global data, global model, and global observation. And the next thing is, without sharing of data, research in weather and climate sciences, it's impossible, right? Suppose I take a station data here, right? Can I make a map of temperature map of India? No, I can't do it. I need data from somebody who is doing the same thing in Bombay, same thing in Delhi, so you need actually a center which collects all the data and then distributes it. It's as simple as that. Otherwise, I'm only talking about even India, but think about, you want to make a global map of temperature, right? So you need to actually, then countries have to come together and put the data together and distribute it. So there has to be a lot of protocols. You can see the complication of the problem. So why data use, data is important. So WMO is the World Meteorological Organization. It actually played a very important, this is before climate science became a big deal. Weather, right? Every day you want to know how is the weather around the world today. Suppose you are going to some other city, you want to know what is the weather there, right? So not only that, also you want to forecast the weather for next 4 or 5 days. So in the weather forecasting problem, initial condition becomes very important. So the data has to be, so the way this works right now is, World Meteorological Organization collects the data from all over the world, and it also distributes to all the weather forecasting centers. Anyway, so since this is about climate change, I'm not going to talk much about this the weather collection problem. And the next one is, without the use of climate models, right? Many people actually have questioned the accuracy of climate models, and are they useful? They are wrong. A lot of things you hear about. I'm going to put a case why they are important. The first thing is, you want to understand, let's say, if I do something to the climate system, how are you going to understand what it's going to do? Unless you have a model, you can't go and do the big experiment, global experiment. In fact, even putting carbon dioxide into the atmosphere, it is a global experiment that started with industrialization. So, but that was interestingly an unintentional intervention in the climate system. But if you want to, let's say, understand, if I remove all forest on this planet, what will be the climate? Can we go and cut all the forest in the world? No, we can't do that. So you need models, as simple as that. So because this is our home. You can't destroy our home by doing experiment on it, right? So you need models, okay? So I'll come to more about model later. And finally, model intercomparison projects have been instrumental in assessing the robustness and uncertainty in climate projections. I think those are the very important thing. Why we need the model intercomparison project? Because each model is telling you different things. So you want to actually bring them together. And the main thing is, that means it can help us to understand which projections are robust and what's uncertainty in projections, okay? All right, I think before, some of you may know this, weather, climate variability, and climate change. Weather is basically instantaneous state of the system. For example, you look outside, it's sunny. So sunny is a description of the weather, right? You can, of course, describe it by humidity, temperature, pressure, cloud cover, etc. So weather prediction is an initial condition problem, and I'm sure some of you know that. So here, collecting the initial condition of the atmosphere is very, very important. That's why every day, every 6 hours or every 12 hours, there is an observation about temperature and precipitation, etc., right? And the next one is climate. That's what this talk is about. So it's basically mean of weather over approximately 30 years. That's a textbook definition. Climate, by definition, it's a boundary condition problem. So basically, what's the level of sunlight, right? Or what's the mountain geography? Or what's the land sea configurations? They basically determine the climate. So climate is a boundary condition problem. And next is climate variability and climate change. So this is a real challenge. Many times there is a confusion between climate variability and climate change. So variability is basically, whatever is the fluctuations, in space or time, right, in the climate system, on the order of, any time is something like seasonal or annual or decadal or centennial, whatever time scale you are thinking about, right? And next is climate change. Climate change basically refers to a statistically significant change, right? It could be a trend, right? In, all the variables in the climate system. Typically, it is basically, it comes from external forcing. Suppose you just brighten the sun. Very simple. Obviously, the climate is going to change. The planet is going to get hotter, right? So, similarly, if you put more carbon dioxide into the atmosphere, although, it sounds like an internal variable, but for the discussion, carbon dioxide increase or aerosol, putting aerosols into the climate system is considered as an external forcing. If any of you have problem with that definition, you can come and meet me. Now, here is the pictorial representation of climate variability and climate change. So you can see here, this is something like approximately 50-year period, right? And so this is the pre-industrial period. You can see the years from 1860, something like up to 1920 or something like that. So the system, this is a simple number from the climate system, that is annual mean temperature, let's say, right? So you can see that it is oscillating about this dashed line. So this is basically pure climate variability, all right? Now, if you look at beyond the last 50 years or so, there is a trend, definitely, right? And at the same time, you can see that about this line, there are fluctuations. I think this has created a lot of confusions. For example, if we are here and suddenly you can see sometimes the temperature can go down for a couple of years. So this actually climate deniers would come and say, oh, look, this year has been extremely cold compared to last year. So where is climate warming, right? So that's because of climate variability. So because of this variability, so the actual time series is this black line, you see this here, right? So it has both trend and variability. So we need to be very careful to distinguish between the trend and the variability, okay? All right, key definition, I think what is global warming? This term is now very popular. I want you to be actually exactly be clear about that term. It really means global mean surface temperature of our planet. It does not refer to a temperature at a single place, single location, or a single state, or a single country. It really refers to the global mean surface temperature of the planet, change in that, right, with reference to this particular period in the latest IPCC assessment report. So that's the pre-industrial period as per the definition in the report, right? And next is human or anthropogenic activities. You hear about this anthropogenic climate change. So what is that term? It really refers to, mainly in this case, mostly fossil fuel emission. For example, we get electricity from coal. We get our, we run our cars using petroleum. And then mostly in Europe and North America, in the winter time, the homes are heated using natural gas, which is also a fossil fuel, right? So it's mostly composed of methane. So when you burn these things, you release carbon dioxide, methane, etc. And there is also deforestation. If you cut the forest, what happens is eventually it decomposes. When you decompose, that CO2 actually gets released to the atmosphere. So nearly, in fact, 1/3 of the forest on this planet has been actually deforested because of human activities. And today, if you look at it, nearly 90% of our carbon dioxide emissions come from fossil fuel burning, and 10% comes from deforestation activities, okay? Now, greenhouse gases, carbon dioxide, methane, these things trap IR radiation. That's the reason why, they cause global warming. And industrial era, that's basically anything after 1850, is referred to as industrial era. That's when, industrialization started in Great Britain. Okay, key IPCC messages, these are the simple messages. Many recent changes in the climate system are unprecedented in the at least last 2000 years. This statement specifically refers to global mean surface temperature, okay? Now, effects of global warming are felt in almost all regions around the world. For example, if you take Australia, every Australian summer you hear about wildfires, right? In India is okay. We don't. I think we do hear about extreme rainfalls, but countries like U.S., Canada, Europe, you do hear a lot about during their summertime heat waves. Okay. Now, I think this is the first time IPCC basically put this term. It is indisputable. That means it's 100% sure that human activities are responsible for global warming. And this, these two messages actually are buried. But I think, these are, to me, scientifically the most important message. That is, the regional changes would increase with increased level of global warming. What that means is there is a scaling, linear scaling between regional change and global change, which means really, if you know pattern of climate change for a specific temperature, you don't have to worry about regional change for any other global mean warming. You can simply scale it, right? So suppose I know temperature change in a place, let's say in the Arctic region, as 2 degrees for every 1 degree of global warming. Then I know for a 5-degree global mean warming, Arctic will be approximately 10 degrees warming. So this scaling is very important. So this is what we call as pattern effect, pattern scaling, okay? So I'll come to this, with a graphic illustration. The next one is every ton of CO2 emitted into the atmosphere would add to global warming. Every ton, you think about it, okay? So it's going to, so that means the more you add, global warming will be more. That's all, as simple as that. Okay, so a couple of graphs I have. Oh, it's not coming out well. Anyway, I think I can just show you, this is basically over the last 2000 years. So what is shown is the global mean temperature anomaly. So in fact, in the last 2000 years, 1900 years, years, the temperature was actually slowly cooling. But suddenly, somewhere around 1950 or so, you see this. So this curve was called the hockey stick curve. because most of the warming happened in the later half of the 20th century. Now, so this kind of warming you don't see in the last 2000 years at least, right? I think that's the message. And here is well, I think the shading is disappearing, but let me just explain what this curve is. So these are the observations, these black lines. These orange lines are basically model simulations when the effect of anthropogenic activities or all anthropogenic activities are included. And this line shows basically same climate model simulations when they were not forced with anthropogenic activities. So these simulations are basically forced with only solar variability and if there is a volcano, which is a natural event. Okay, so basically this proves from a model perspective that human activities are responsible for global warming. All right. Now this is that scaling that I was talking about. You just look at this figure very carefully. This is if the global warming is 1.5 degree. This is for 2 degree and this is for 4 degree. You can see the pattern remains the same, right? But the amount of warming at every region, it actually increases. So in fact, if you can take a look at the report, it's called pattern scaling or pattern scaling, this pattern scaling concept. So anyway, again, this is for 1 degree observation and this is 1 degree warming model. So models are able to simulate the historical climate change, and once models are able to do that, then of course you can use them as a projection tool. And so these are the projections for up to 4 degree global mean warming. In fact, I think I'm showing you can also see this. There is no scenario in this. What's the future scenario? That's not shown in this figure, and also no time frame is given. It doesn't matter when this 4 degree warming happens or on what socioeconomic scenarios we are in the future. What really matters is what's the global mean warming. All right. So that concept, you can see that concept working even for precipitation change. So this is 1.5 degree future, this is 2 degree future, and this is 4 degree future. So you can just see that the changes become larger and larger with the amount of global mean warming. Yeah, I know it's a very complicated system. I'm really trying to simplify, okay? So, or I'm just only selecting the results which are actually simpler, okay? So the next thing is even extremes. This is basically averaged over all the global land, okay? So you can see here there are two, box and whisker, things here. So the blue one is basically 10-year event. I'm sure civil engineers know this. 10-year event is basically a temperature event that occurs only once in 10 years, the highest warming event or whatever. So there is also 50-year event, right? So you can see again, these are levels of warming again, 1 degree, 1.5, 2, 3, 4, right? So again, you can see the intensity of these extreme events. Again, almost linearly, it goes with extremes, right? And this is frequency. Frequency also, it actually scales with global mean warming. And finally, for the IPCC message, this is a simple predictor for climate change. That is, how much carbon we have, carbon dioxide emitted into the system since the pre-industrial time. In fact, there are papers, you will see that if you put 1,000 petagram of carbon, which is gigaton of carbon, the approximate warming, global mean warming is about 2 degree or something like that. So if you put 4,000 or 2,000 petagram of carbon, the warming will be 4 degrees. So again, this is a linear scaling, right? So you can see approximately this is linear. So this is the cumulative CO2 emissions in billions of ton, and this is the global warming. So that's a kind of linear thing. So now a little bit about one slide on the policy, okay? So this is basically gross world product. This line here is the gross world product today is about 120 trillion US dollar. I'm sorry, this curve is not being, this is the carbon dioxide emission. So the carbon dioxide emission per year. So there is a close relationship between carbon dioxide emission and the GDP, that is, global GDP. But of late, you can see that this is actually slowing down. So what it is telling you is that for the same carbon dioxide emission, we are actually able to produce more services and more output. This is actually happening because of efficiency in energy usage. Basically, with the same energy, we are actually producing more. Unfortunately, to produce the same energy, we are still emitting the same carbon dioxide. I mean, I think that's what I have written here. That is, slower growth in C emission is because we now produce more with less energy, but carbon dioxide emissions per unit energy has not decreased. I think that's and another thing that you have to actually understand based on this curve is, if you want to stop warming, this, I mean, somewhere around right now we are emitting 40 gigaton of CO2 per year. This has to become zero. When people are talking about net zero, we are really talking about taking this thing to zero, right? So the goal right now is, there is a lot of push at the global level to bring that red dot to zero by 2050. Anyway, I don't want to pass any judgment on that, but it is really hard, right? From that point, how to reach zero. Okay, so now, how do we get all this assessments, right? So what is behind all of these assessments? Number one, observational data sets. I'm specifically referring to the scientific assessment of climate change, right? So global data sets. So there are various sources of this global data, and then climate models. So this data is partly I would say open access, not fully, and then we have climate models, which are again mostly not open to access. That is, only few modeling centers really have the resources. If you want to actually make it open access, again it takes a lot of resources to spend on it, right? Because people are going to send you questions. So you have to answer to them, right? Suppose there is something not working in the model, you have to tell them. So there is a lot of modeling centers are not equipped to handle that. So most models are private to their modeling center alone, but some models are openly accessible. And next one is, I'm going to mostly talk about this model intercomparison projects, okay, which is mostly open access. All right. So a quick introduction to the data. I have only 3 slides on this data. So it just tells you, the data collection started, really instrumental data collection started somewhere, around the industrialization period. So basically, as rudimentary as just a cloud, just to visually look at it and record it. I mean, that is also a data, right? And then kites. You send sensors basically through kites to measure the temperature at various levels. And then as technology got sophisticated, you have these balloons, pilot balloons. And here is the huge transformation in data collection. Basically happened in around 1980s, or to be precise, 1979. So satellite era basically started here. So this made a huge difference in data collection, because you are actually seeing from the sky the whole planet. You are able to see, and the amount of data generated is humongous. In fact, NASA, for example, was collecting this data, right? I don't think they could actually really analyze all of that data. One of the reasons they gave out the data is basically these centers don't also have resources to look at everything, right? So if they throw out to the university community, the university faculty and the students, they can actually do some good science. That's one reason also behind most of this data actually coming out to the public. So again, okay, the next is this figure shows the starting date of temperature observation. For example, you can see in Europe and North America, the data collection started somewhere around, beginning of 1900 or something like that. But still you can see there are lots and lots of area where there is no data collection at all, particularly the ocean areas, right? Ocean area, Africa, the data collection is poor. And this figure shows how many satellite-derived data products are today available, right? So these are basically meteorological products or climate products that any researcher can actually use. So you can see this is only so this is 1980, 2000, 2006, or yeah, this 2000. So even somewhere around 2010, something like 50 satellite data products are available. These are different variables of the climate system. Now this is just an illustration of how much data is actually produced by satellite versus everything else. Okay, so this is instrumental data collection. It's mostly confined to land area, hardly any data over ocean, but this is satellite scanning. It just goes around the planet, right? Now, at a specific particular time here, 7th April 2016, this is the number of data that is available through satellite, and this is through everything else. So you can see an order of magnitude difference at any instant for data from in a day, right? In a day, data from stations and the satellite. Okay. Then there is also data, paleoclimate data. There are various. This is basically for people who are doing paleoclimate science. I'm sure most of you must have heard about tree rings. Tree rings are basically used. You can, if a tree lives 500 years, you can actually chop it and look at the past 500-year climate, right? So the time scale is about hundreds of years. And then ice core data. Some of you may have heard about ice core data. Ice cores basically allow us to look at atmospheric CO2 composition in the last 1 million years or so. Okay, and then I think the most you can go is something like you can see here 100 million years. So this is basically marine sediments. So you can actually look at the climate over 100 million. Is that right? Million years? Yeah, 100 million years. Yeah. Okay, so that's briefly about data. All of this data is basically, some are shared, some are maybe people keep it to themselves. And the next thing is climate models. So basically, there is a hierarchy of models. So let's not get into that. So today, what models are used? Basically, 3D GCMs are used. This is just a representation. Basically, you have the grids on the horizontal as well as the vertical. Today's atmosphere models, they have about 50 vertical layers, right? And the horizontal resolution is anywhere from 1 degree to 3 degrees. 1 degree is 100 kilometers to 300 kilometer horizontal resolution. So you just put this grid and you solve. I know many of you think of fluid dynamics, but today's models, we are way past fluid dynamics. Fluid dynamics was a major research problem in climate modeling research in the 1980s. Now it's really putting various physical processes, biological processes into the models. Okay. In fact, you can see in this a little bit almost 10-year-old slide from the previous IPCC assessment. So today's models basically they do all the atmospheric processes, land process, ocean and sea ice, aerosols in the climate system, carbon cycle. Carbon cycle basically, here main thing is, some of these models actually do photosynthesis also. The photosynthesis representation is there in the models. And dynamic vegetation. Dynamic vegetation, what it refers to is that if the climate is not suitable, let's say for a particular forest to thrive there, it can alter that type of vegetation that will, basically the climate would support there, right? And then atmospheric chemistry. So today, in fact, this is the biggest thing. There are models with close to 200 levels in the vertical, mostly in the stratosphere. So they do this, stratospheric chemistry, and then the last bit of piece that people are right now working on is ice processes. Ice is basically, you have this huge ice sheet in Antarctica, for example. The mean thickness of that ice sheet is 1.5 kilometer, just to give an idea. All right. So in most of the projections so far, these ice sheets were basically fixed. They were not changing with the climate and all that. So now people are actually, modeling centers are trying to basically make these ice sheets interactive with the rest of the climate system. Okay. Okay. So now some very important remarks about climate models. What are really models? Models are basically, climate models are created to, I think this term is very important, approximate the real world. So we do not go and do the experiment on Earth itself, right? We can't do that. Models are basically digital analogs of the Earth, right? They are just a replica. You are trying to replicate the Earth, right? And next thing is, we will never be able to. And right now, of course, we don't know how to model every physical, biological, and societal process. Precisely is important. If you know precisely to model all of them, of course, you would create exact replica of the Earth. But we are not going to. In fact, I can tell you, at least in my lifetime, it's not going to happen. All right. So even the biggest supercomputers you have today, you can't really put them precisely. Okay. So for using them as predictive tools, but you have a replica, right? It's not going to be perfect, but it's going to be close, right? I think that's the whole idea of the model, any model, right? Now they have to be, of course, number one, compared to the observation, because I mean, how is your digital analog? You have to do that with the observation. And another thing is, interestingly, there are many modeling centers around the world. So that means today there are about probably, I mean, there are many versions of the model, at least something close to about 30 or 30 plus modeling centers, okay? And each of these modeling centers also have many versions of the models. So if you include all of that, in fact, if you go to the modeling intercomparison website, more than 100 replicas basically participated in this model intercomparison project, right? So the idea is the following: why we do this? Main thing is, as I already discussed, robustness, uncertainty. That actually this provides that particular estimate using models, and also if you have, let's say, 100 replicas, and you, let's say, do a evolution, what's going to happen in the future, you are really going to have an ensemble of models, right? So you are going to have really an envelope of projection, not a single line. Now, in fact, you can do this backward. That is, since we have data now, you can actually do the forecast starting from, let's say, 1950 to 2020, 70 years, right? I think that I'm okay if this observation falls within that ensemble of evolutions. I think that is what so basically observation should be within this envelope of digital analogs. I think you get the idea why multiple models are important, right? Okay, now a quick history. When this started, in the 1960s, 70s, and 80s, models were getting developed in various modeling centers, right? UK, France, Germany, US. Now, you do a particular problem. The simplest problem is, suppose in these models, you double the atmospheric CO2 concentration. Now, some models give 2.5 degrees global warming. Some models give 5 degrees global mean warming. Some models were giving just 1 degree warming. So this is where there was confusion coming around, right? In the 1980s, there was confusion. So what's the real answer? Which model is actually close to the Earth? So US Department of Energy supported this first program that's called AMIP. That is the Atmospheric Model Intercomparison Project. It started in 1990. So this really started as a research exercise, okay? Because they wanted to see why models are actually doing differently. You want to understand what's different in the model. Why, let's say, some model is giving 5 degrees warming, or why some model is giving 1 degree warming. You want to understand what is the physics in the models that is different, between them. All right. This was a huge success, but that was only for the atmospheric component. It was not a coupled. Coupled means, you need ocean, sea ice, everything should be there, right? So this was a success at that time, 1990. But then they wanted to extend this success to coupled model. Coupled is basically atmosphere and oceans are coupled. So you have a single model that basically where the atmosphere and ocean and sea ice, everything interacts with each other. But this was a slow process. You can see that 1995, within 5 years, they started this coupled model intercomparison project. And then there was also 1997 CMIP2. But this was a quiet activity. So then what happened was sometime around 2005, that is almost 15 years later, I think there was this proposal that IPCC assessments actually started also in 1990. So there were already three IPCC assessments have happened. So for the fourth IPCC assessment, I think there was a decision that let's use basically this model intercomparison. So basically, of course, we were getting more computing power. We were able to handle lots and lot of data. So this was the proposal, and basically first time, the fourth IPCC assessment actually used this CMIP3 data. I mean, in a sense, this was the first statistical assessment of climate change in the IPCC reports. Okay, and then after that, in 2010, CMIP 5, and then we had this IPCC report based on this in 2013, and CMIP 6. CMIP 6 was the latest one. The planning of started in 2018, and the report came out last year. Okay, now why is this? What is the organization of this? Of course, it has to come from the top level. So this is really supported by United Nations, right? I mean, a single government cannot do that. So really, you have to do through this multiple countries together, right? All right. So you have this United Nations, which basically supports this World Meteorological Organization, which basically sponsors WCRP. WCRP is basically World Climate Research Program. So it has a working group on coupled models. So this coupled modeling. So basically, this working group was assigned organizing this particular model intercomparison exercise, which basically what this means is you need to invite all the modeling groups and ask them to design a specific experiment. So that means everybody would design the same experiment, and everybody has to produce. You can't produce, the models produce enormous amount of data, right? So there is a protocol. I would simply put it as a protocol. There is a protocol, so you have to run those experiments and you have to actually produce those specific data. And once your simulation is done, send it to a centralized location. All the modeling groups have to send it. And then when AMIP and CMIP started, I think initially we were, if you are a user, you have to write a small proposal to use the data. But then I think with time what happened was people thought, well, even that's not needed. You just go and register and just start downloading data. So that's what happened with this CMIP 3. CMIP 3 basically is the first time when anybody can just go and start the modeling. They can grab the model data. So how much time we have? All right, maybe 10 more minutes?
5 more minutes.
Okay.
This hall is booked for some other purpose.
Okay. So CMIP 3 was the huge success. Basically at that time, anyway, still it was a coarse resolution data. So data from modeling centers collected during 2005 and 6. Data is free for non-commercial use. So any academic person can download. The data size was only 36 terabyte. But remember, at that time, 36 TB was huge to store it and safely distribute it. It was really a big deal at that time. 40 terabyte was really a big deal. I mean, I'll come to today what that size is. So IPCC AR4 was, this one, basically this IPCC report won the Nobel Prize and all that. And also, there is a center that collects, what publications. So you can actually tell them, whether you use this data. So around 600 publications actually came out. For CMIP 5, the number of experiments and, it just became too much. You can already see so many experiments described in these boxes. All right, that is CMIP. And CMIP 6 is even worse. It just got humongous. There are so many, these are all what I call as sub-MIPs. So there is this MIP project, and then under that, suppose somebody wants to only understand how aerosols are simulated in models. So they have this, where is that? Aerochem MIP. Suppose somebody wants to only look at carbon cycle, then there is a C4 MIP, land surface MIP. So there were actually 21 model intercomparison projects under what was single MIP before. Until CMIP 5, it was coupled model intercomparison project. Everybody has to do whatever. Now they branched out, so these sub MIPs are available, and so this is the summary sheet for CMIP 3, CMIP 5, and CMIP 6. So originally CMIP 3 was only 36 terabytes. CMIP 5 grew to 1.5 petabytes, and today it is close to 24 petabytes. And the number of publications you can see, CMIP resulted in six. So these are all free data. So people got free data, and then this is 1400. So this, statistics has to come. So this is the, how much data has been downloaded so far as of today by various continents. So in the US, 14.5 petabytes of data has been downloaded. Europe here. Even somebody in Antarctica has downloaded the data. All right. So I think there is a proliferation of MIPS now. As you can see, there is also a regional, whatever I have discussed so far, they are all global models. There are also models that are, focused on regions. So there was this exercise called CORTEX, Coordinated Regional Climate Downscaling Experiment. So here basically, in India, for South Asia, Indian Institute of Tropical Meteorology they are in charge of doing this particular multimodal exercise. Yeah, here is the number of modeling centers that contribute to CMIP and CMIP6 and CORTEX. So anyway, so the number of modeling centers are, too many now. Yeah, I think India also, there is, where is India here? Oh, I'm sorry, I'm able to, okay, anyway, there is a modeling center from India that is in Pune. All right, so, I have, I'm not actually an expert in CMIP5, let me tell you that, because I use actually always single model. Only a couple of times I have, participated in this, research which uses multiple models. So this is one such research. So we basically compare multimodal mean with the observations and then projections. So this is for India from the previous IPCC assessment. We basically looked at what's the temperature change and the precipitation change projected for India. We looked at also for Karnataka, and this is for one of our students. We looked at a particular basin, how glaciers would basically disappear with time. Again, multimodal based assessment here. So basically we took ensemble mean projection from these models, and we used that basically data to drive glacier estimation. So we see that how glacier area is shrinking with time. All right, but I think what has happened is this is now extended to even impact assessment. For example, suppose I have a crop model which can tell me how maize or rice or wheat yield will change under climate change. So what people do now is, instead of people used to actually drive those models by climate projections from a single model, but now that's definitely not right. So now people drive with a multitude of models, and then you get a, unfortunately the shadings are not coming. So you get a range of results rather than a single result. So in this case, for example, there are 5 global models and 7 crop models. So you basically have 35 crop yield projections. So you basically look at the range of projections for, lastly, I think just for fun I put this. Look at the number of authors in this paper. Again, this is a global ecology. This is not global climate problem, but this is a global ecology problem. So basically, this paper is about counting number of tree species on this planet. So obviously, people have to pool data and share. So, so I just, this is one paper where I participated in a MIP project where I shared the data. So I think one side result of that is typically climate, if you look at climate change papers which use these multiple models, you see authors on the list order of anywhere from 20 to 50 authors you see normally in these papers. All right. So, and even, this is a climate change assessment. In the latest IPCC, there were about, in the working group 1 assessment, that is a scientific assessment, close to 250 authors from 65 countries, right? And you can also look at the number of review comments. That particular report, basically, it's a 4,000 page report, I believe. So basically, number of countries basically commented. Okay, I'm in the final slide. So climate change, research globally is coordinated. I mean, driven really from the UN, right? Basically, WMO and UN, United Nations Environmental Program. And open access to data is one of the key reasons for the success of climate change in the last 3 decades, okay? Basically starting from people are thinking about how to do this. So it took maybe 15 years to basically to have the computational power and all this, number crunching power, okay? And finally, MIPS have provided an enormous opportunity for a statistical assessment of climate change. I think for me, when when we did the first assessment in 2007 using this multiple models, it was, it's a huge challenge to get to that in 2007. At that time, the number of models were limited, and the data was, as I said, only about 40 terabytes. But today, I'm not sure whether that kind of organization is, right, with so many sub-MIPS and things like that. It is confusing, yes. That's all I have. Yeah, sure.
So we do have to leave this place in a short while, but we will still have a few questions.
Yeah.
Sir, thank you very much for the very enlightening talk. India is planning to compete with China to become a global hub for manufacturing. Wouldn't that be a disastrous for us in terms of climate impact that it will have on us? Because we are going to use a lot of electricity for that, and we are still generating a lot of fossil fuel-based electricity.
Yeah. So, I understand. I think, this is why net zero, for example, is, a lot of countries were kind of under pressure during the last, what is called COP. COP meeting is basically Conference of Parties. The next COP is in Egypt this year. I think sometime it's going to happen. So India has given 2070 as the net zero, which means, we have 50 years to basically, bring our carbon emissions to zero. But in the meantime, our emissions will keep going up. And then we have to actually start reducing the emission. Now, the way you can do that is renewable energy. I mean, that is the hope that many are counting what I would call as in two simple terms, emission reduction. So you reduce the emission, but it's a huge challenge. For example, even this year, for example, it's really kind of laughing in some sense. A lot of European countries were now under serious problem because the Russian gas was not going there. So they were thinking of even, restarting the closed coal plants. So, I don't want to get into the, it's a huge challenge how you would reduce the emission. And also there is, I don't know if you have heard of it, I didn't cover that here, carbon dioxide removal methods. For example, people have proposed we would artificially, directly from the air, remove CO2 and transport and put it into underground storage or something like that. So in fact, the IPCC, the third working group report, it heavily relies on this. If you, for example, you want to reduce, I would say, let's say this 1.5 degree goal, right? I mean, the Paris Agreement was 2 degree was the goal, and the ambitious goal was limiting global warming to 1.5 degree. If you look at very carefully the emission curves for that, we need to actually, the global emissions have to become zero in 2050, and after that it has to become negative emission. So what is that negative emission means? Basically, we have to bring the CO2 down in the atmosphere. Instead of going up, it has to start coming down. For a 2 degree warming, the net emissions have to become zero in 2070. And after that, again, the carbon dioxide emission has to rapidly come down. I don't want to really get into this, distant future. But for many governments right now, it's really a challenge. That is, for many of us, actually, many Western countries, the emissions have to peak by 2030, and it has to start coming down. But they are actually able to do it because I think Europe has been very successful in this. In fact, their emissions have been coming down in the last couple of decades. And in the US, actually, it has plateaued, right? But they all have to bring it down to zero. Plateau is not enough. You have to really bring, as I showed in one of my earlier graphs, we are very high right now. We have to bring it to zero. I don't know. I have, I'm not an expert in that area. So, because, it is about how, again, you are asking a question on social science and policy, because that really depends on how we are going to respond in the future, which I don't know. But it's needed. Yeah.
Yeah, so this crop models is helping in the agriculture field.
Yeah.
How these crop models are helping our farmers to increase the yield and other things?
Oh, crop models. No, I think what I was basically referring to is not these models. I think when you are talking about yield increase or let's say climate resilient crops and things like that, I think that comes from field research. You basically create a slightly genetically modified version of the crop that can, let's say, withstand heat. You anticipate the future the heat is going to be more, right? So you try to basically genetically modify the crop that would withstand the heat and things like that. But what I was talking about here is the crop models, which can tell, okay, in the future, if rainfall is reduced by, let's say, 10% and temperature increases about a couple of degrees, how the crop yield is going to change. So these models are basically, representation of crops, crop photosynthesis and things like that. And they are detailed model, but they are not actually going to, I'm not talking in the context of how you can change the crop colors, there are things like that. So, yeah.
So, when you have different types of models, so how do you assess the correctness of each one of them? Because you have to integrate them. So, if some models are not not capturing the realistic picture as one thinks of.
Yeah.
So
there is no consensus on that. This is what is called weighing the models.
Yes.
When you make an average, do you give larger weight to models who are close to observations versus giving very low weight to models which are way off from observation. I think people have argued for this, but so far every model gets us equal weight, because again, it gets into politics. Suppose your modeling center is, let's say, okay, that is one issue. But also, I think there is no very clear-cut way of weighing the model. That as simple as that. I'll tell you why. A model may be, let's say, doing extremely well in simulating, let's say, Indian climate, right? But the same model may be doing extremely poor in doing the polar regions. So the big question is, how do you call a model good or bad? What is the metric you have? That itself is a problem. Because there are so many variables in the climate system: mean in temperature, mean in precipitation, mean in winds, mean in surface pressure. So some models may be doing some of them good. And then next, some models may be doing all the means good, but they may not be doing the variability in the climate system well. So this is where the challenge has come. They are not. We still don't. People have done all kinds of weighing schemes. So far, we don't have a successful weighting scheme because of this too many metrics to evaluate the models. Right? It's possible, right? Some model may do extremely well Indian monsoon, but the same model may not do well Australian monsoon. Yeah, such problems are there. Yeah.
NASA, what is just provided like a very low resolution data, like a 0.25 degree resolution. When we come into the very like a regional analysis time, we have required very high resolution data.
Yeah.
What we have to do that kind of?
No, now there are global models which are run at even 25 kilometer resolution. In addition to that, I had a slide on what is called Cortex. Cortex is basically regional model, where it's a regional model intercomparison exercise where regional models are used. I think the highest resolution, the regional models, I think in that kind of data set, I can just only give you a rough idea. It's about a 10 kilometer resolution. That's the best you can get. In this kind of situation, what people do is there is also what is called a statistical downscaling technique. A lot of civil engineers basically use that technique to assess, basin scale water resource problems and things like that. So I know I didn't really talk about how you can do statistical downscaling to the individual regions. You can do anything you want. I think ultimately, you have to, of course, compare with the, suppose even if you produce, let's say, 1 kilometer data, then of course you have to really compare with the observations and make sure the model is actually, your statistical or dynamical downscaled data is actually in good agreement with observations, etc. Yeah.
Yeah, one more question, sir. And I'm using like a high resolution modeling, and I'm using like giving the initial conditions and boundary conditions like a GFS data. It will giving the output like 1 kilometer resolution, as well as I wanted to compare like with observational data set.
What is the model? This model?
The WRF model.
WRF, okay.
It will give the observation. It will give the data, and I want to compare the observational and this data. It will give some accuracy results. And one more thing I noticed that can we add this data like observational data and what is given the model data? Can we combine?
How do you?
In data assimilation process.
No, you are actually okay. Yeah, I think you are using WRF, right?
Yeah.
And how long are you running?
From giving like a daily focus.
Yeah. So yeah. Okay, that is a weather forecast problem that you are talking about, right? I'm not really working on that, but I can maybe attempt to give you an answer. Yeah, WRF actually can be, it's a weather forecast and research model, right? Yeah, WRF, weather research and forecast model. But it's really, as you said, it is used for weather forecasting mainly, right? For example, for India, you can configure that model and give next 5 days, 4 days, 5 to 6 days weather forecast. Again, same technique you have to use. You have to again come up with a metric that evaluates the model's skill in forecasting whatever domain you are looking at. So again, that skill is based on a comparison with the observed data, observed weather data. You have to do that.
Yes, sir.
So
station data.
Yeah, station data. Well, or gridded data. For example, IMD gives you gridded data in precipitation and temperature. So you have to. I think generally a good thing is at least you first over the complete domain you should create a metric and see whether it is doing it right, and then you have to come up with a spatial pattern, a metric based on a spatial pattern and things like that. And only when you are sure that the skill is reasonable. There are a lot of papers on that. There are a lot of definitions of skill scores. So you need to meet one of those conditions, and then once you are reasonably confident that your WRF is able to simulate the regional climate, regional weather in a reasonable way, then of course you can be confident about its future. But in this case, are you thinking about only weather forecast, or what are you trying to understand?
Yeah, like I want to do like weather observational data sets and like what given the model data, we have to combine. It will give like a high accuracy results. It will be possible or not?
No, that is you are talking about reanalysis kind of thing. I mean, you are assimilating the data and you are trying to create a data product. Yeah, that's a different kind of problem. That's a reanalysis. There is a whole story about reanalysis also, but maybe we can.
I also suggest that we take the discussion out to the high TA.
Thank you.
Yeah.
Because we are running out. It's my pleasant duty to say thank you to Professor Bala for this wonderful lecture. And so as a token of our appreciation, I have a little memento to give him.
Yeah, thank you.
Thank you so much.
Yeah.
And yeah, thank you all for coming, and we will break for high tea now.